Okay, welcome everyone. Welcome to June's Rust London virtual talks. My name's Ernest and I'm going to be your host for the evening. Thank you all for coming on this lovely hot day. So for those of you who may be honorary Londoners for the day, who have just been coming to the Rust London meetup for the first time virtually, here's an introduction about who we are and what we do. This is the Rust London user group. This is the Rust London talks. We have this meetup every month, and it allows the London community to get together and showcase what's going on. We showcase projects from companies as well as individuals, and it's meant to be a place where we share our learnings, share our experiences, and get to know each other. This is one of the 3 meetups that's run by the Rust London user group as a whole. There are 2 other sorts of meetups that are run in conjunction with the London talks, and they are the Rust London Code Dojo, which is run by Luca Palmieri of TrueLayer, and we also have the Rust Hack and Learn as well. The Rust London user group supports the London ecosystem, which has only been buoyed by the explosion of Rust in production in the city. So we're seeing a number of dev shops, we're seeing a number of companies adopting Rust in London. And that's allowing our community to grow and become more vibrant and just become a lot more fun. So here are a few companies that are using Rust in London and in the UK wide. We also have an honorable mention of One Signal, who are celebrating their 4th year of using Rust in production. They're not based in London, but they're an honorable mention to show how far we've come as an ecosystem, as a language, and as a community at large. The focus of the Rust London community, in light of everything that's gone on, this crazy year, right, has always been to be a welcoming place. The focus for 2020 is still, regardless of whether we're in a physical location where we can all meet each other in person, or we're doing this virtually, is to be a welcoming, open place for people of all programming levels to empower themselves with the Rust programming language. And that leads on to our code of conduct. The Rust London community has signed up to the Berlin Code of Conduct. And all that really means is that we have a set of rules that just make sure that we interact with each other with respect, and we're kind to each other, and we're welcoming to each other. As a community, we always focus on the tech, and we focus on where we are as a community, as an ecosystem with the Rust programming language. One of my biggest draws, and the reason why I'm so proud to be a part of the community, is the diversity that we have. And this is reflected in our speakers, in our community at large. So let's just all focus on just being respectful and kind to each other, and yeah, just don't be an idiot. All right, thank you. And as always, please feel free to use emojis, fire emojis, clap emojis, and crab emojis when we have speakers, because we're missing that actual in-person interaction. You obviously can't clap as an audience, but please show off in the groups with your memes, with your clap emojis, with the fire emojis, and all the rest of it. The way questions and answers will work with the meetup is it will work as a panel session at the end of all of the speakers. So there won't be any questions at the end of each talk. There will be a link to Slido, so you can use the QR code, or you can go to slido.com, use the hashtag and the passcode, and you'll be able to ask your questions. They'll be collated, and then we'll have a panel session at the end where all of the questions will be asked to the relevant speakers. It's very, very important as well that we know which question is to which speaker, that when you're writing your question, you address it to the speaker that it's relevant to. If it's relevant to more than one speaker, then you can leave it as an open question. But if there is no name attached to a specific question and it's not clearly obvious, it will be treated as an open question. So please remember, if your question is specific, directed to a speaker, make sure you attach their name beforehand. So please use a QR code, go to Slido, and that's where your questions will be collated. It's really, really important that you follow us on Twitter. So please, everyone who's on Twitter, it's at Rust London users or at Rust LDN users. The hashtag for the event is Rust London. So please, 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 everyone jump on Twitter. Follow us if you're not following us on Twitter. Also, the YouTube is up. That's where all of these videos will be posted. So if you go into YouTube and just type in Rust London, you'll see the channel. Please subscribe away there as well. But Twitter is the best way that you can interact and generally keep up with what is going on with Rust London. And YouTube is where all the videos will be placed after this. So again, because we can't be in person and we're doing this virtually, it's still cool to keep up the tradition of after meetup drinks. So if everyone after the event could follow us into the Discord room, we're going to have an after meetup pub in the Discord room. So bring yourself a drink and we can have a virtual after meetup catch up. It's a place to network with people. The speakers will be in there. So if you didn't get a chance to ask a question, you can ask it to the speakers in the room. There'll also be a bunch of us just hanging out in the Discord channel. It will be in the main Rust Discord channel as well. So the link to the Discord channel is in the description of the YouTube video. And after the meetup, you can follow us in there and we can have a virtual after meetup pub drinks. So here is the order of today's speakers. We're going to have some news and some announcements, and then we'll have our first speaker, Tyler Zhang, followed up by our keynote speaker, Erich Schudt, and we'll close out with Alec Mocatta. Okay, so here are some community announcements. We're going to start off with some job postings. So all of the speakers from last month are still hiring. And we also have some other job postings that I found just through Reddit mostly. There's a really cool thread on the Rust Reddit page. There's a thread where everyone who's hiring specifically for Rust, or it will be a full stack role with opportunities to learn the language and work with Rust is there as well. And I've picked a couple of them from there. These are jobs that are going to be specifically related to the London community or are remote. So there's a bunch of other jobs on the Reddit feed as well for all over the world. But these ones here are the ones that are specific to the London and are pertinent to the London community. So please take a photo of this. Here are the websites. There are a bunch of people hiring for Rust or Rust-like roles. Second big announcement. So Rust Warsaw are going to be having a virtual Rust conference. It's going to be a 7-day Rust conference where they'll have some amazing speakers, there'll be workshops, and there's going to be a hackathon as well. This is going to be a massive deal because it's them really showcasing and filling the gap for, Rust Fest and Rust Conf. and all of the other Rust meetups that we haven't been able to attend physically. So this is going to be the first big Rust conference of the year. And we're gonna have they're gonna be making some announcements on who their keynote speakers are going to be. We're gonna have some community members who are going to be speaking as well. So please check this out. The website and all the other information will be tweeted out as well. And it's actually going to form a part of next month's meetup. So there won't be a Rust London meetup next month because of Rusty Days. And Rusty Days being so late in the month when we usually have our meetups, we don't want to have a clash, or we don't want to cannibalize what they've got going on. So Rust London is going to be fully supporting Rusty Days, and we're going to have some of our community members actually speaking at Rusty Days as well. So that's going to be your Rust fix, or if you need your Rust London fix, that's where you'll get it. So Rusty Days is going to be a 7-day conference from the 27th to the 2nd, virtually, of course. So you'll find all the information on here. Right. So now I'm going to hand over to our first speaker, Tyler Zhang. Crab emojis, clap emojis, fire emojis, please. We're just going to switch screens now.
All right, thank you, Ernest. Hey everyone, my name is Tyler Zhang, and my talk is called Visualizing Physics in the Fourth Dimension. All right, so what is this talk about? As you can see, this is an earnest attempt at writing a fully functional physics engine, but in 4 dimensions. All the objects that you see here are 4-dimensional, and all the physics are 4-dimensional too. Let's talk a bit more about the motivation of this project. So originally, this motivation was by an indie game developer, Mark Tim Bosch's work. He made 2 games called Miyagakure and 40 Toys. And for those of you who don't know, Miyagakure is this 4D puzzle platformer game that's been in development forever. Whereas 40 Toys is a physics sandbox that he made as a result of his work on Miyagakure. These are the only examples of 40 games I found. So the motivation is, well, how hard could making a 40 physics engine be? Also, neither of these are open source. So this would make my project the only 40 physics engine on GitHub, which also means it's the best 40 physics on GitHub, naturally. All right, and before I go further, it has to be mentioned at this point that after I agreed to this talk, Mark Tim Bosch had his paper written about n-dimensional rigid body dynamics accepted into SIGGRAPH, which is an actual super prestigious computer graphics conference. So go read his paper if you want something that goes deeper into the physics and the maths. All right, let's get back to writing physics engines. What do you need for a physics engine, not just a 4D one? Well, the basic update loop is quite simple. There are 3 steps. First of all, where we have to process any collisions that happen in the frame. Then we have to do a physics update, which means like moving the objects along according to the velocity or whatever. Then we have to render them to the screen. Well, we're going to go through these steps in a kind of a funny order. We're going to do rendering first, and then because it's kind of hard to see what's going on if you can't see anything, and then we're going to do physics updates because we need to be able to have like velocities and things actually moving in order for things to actually collide. And then finally, we're going to tackle detecting processing collisions last, which is also the most complicated part. So let's talk a bit about how we're going to render things. Of course, it's not so simple to just render 4 dimensions because we live in the 3D world. There's no way to display 4 dimensions, at least not in just natively. So what are some ways we could try to visualize 4D? One thing we can try is what's called perspective projection. This is where you take some 3D, like for example, in the 3D case, we take some 3D scene, we render it down to a 2D image, and then we just show the 2D image. And this makes sense to us because this is the way we encounter the 3D world. But so you might imagine doing the same thing with 4 dimensions. You take a 4D object and you try to use perspective projection to project it down to 3D. This is where you get this famous image of a tesseract, by the way, where it looks like a cube inside another cube. We're not actually going to spend too long discussing this because it turns out like it only really works with wireframes. Like if these sides were not hollow, you wouldn't be able to see anything. It would just look like a cube. It also messes up like distances and angles. Like for example, these edges are supposed to be all parallel, but they're not. So instead, we're going to try what's called slice projection. So suppose we were 2-dimensional. We could try to imagine a 3D object by taking 2D slices through the object. So if we have this 3D sphere here, you can imagine taking slices through the object and getting a cross section of the object here. And you can see that I've drawn what the cross section would look like in 2D. And you can see as you take different slices through the object, you get different slices. In this case, you get a series of circles, and you can kind of imagine stacking the circles on top of each other and like getting back the original sphere. This is a bit like taking an MRI. Like the MRI takes 2D slices through someone's body, and then you can imagine putting them all together so you get the original 3D shape back. The advantage of this is that it preserves geometry because these things really are circles. But the disadvantage is that you can only see a very thin slice of the shape. You can't see the whole shape at once. But wait, we haven't even talked about how we're going to represent 4D objects yet. In 3D graphics, we usually represent surfaces with triangles because they're the simplest shape. In 3D graphics is in fact all about rendering triangles to the screen. In 4D, however, surfaces are three-dimensional, which is really weird to think about because what? And so we need like a 3D solid to be able to represent 4D surfaces. The simplest 3D solid is this shape here, which is called a tetrahedron. It looks like a pyramid. It's the simplest shape because it's just 4 vertices. And we can always approximate surfaces with tetrahedra in 4D, just like we can with triangles in 3D. So how is this going to work? Well, we're going to represent objects using a mesh of tetrahedra instead of a mesh of triangles. And when we take a slice, we're going to slice through all of the tetrahedra and then figure out which ones intersect and then render all the intersections. So we need to work out how we're going to slice through a single tetrahedron. We can do a bit of a trick to go down one dimension here, because just like how every single triangle is in its own 2D plane, we can think of every single tetrahedron as in its own like 3D plane inside the 4D subspace. And when we take a 3D slice through that 3D subspace, the 3D slice will look like another 2D plane. So we can reduce the problem down into slicing a tetrahedron in 3D with another 2D plane, which is much simpler to think about. And you can see here, there's basically 3 cases. Either there is no intersection between the tetrahedron and the plane, in which case it means it's either fully in front or fully behind the shape, or there are 3 intersections. There are intersections with 3 of the edges, in which case you get a triangle. So you just emit this triangle and render this triangle to the screen, or there are 4 intersections between the edges. And you get four intersections, in which case you render quadrilateral. There are some edge cases here, but we don't really care about those. We're going to just render nothing. Nothing. And so what does this look like in code? Well, from linear algebra, you have like a vector equation for the plane of like any slice plane that you take, and you also have a vector equation for an edge. And you can solve these 2 equations together to get the unknown, and it tells you where the intersection point is going to be, or if there is an intersection point at all. So we can implement this using this Rust function here, and we either return some of an intersection point or none, and then we can just collect those results for all the edges of the tetrahedron, and there we go. We can determine which 2D surface to emit, and we collate all the triangles and we render that. But this is a bit annoying because if you think about how CPUs and GPUs normally work, normally we have to send a whole bunch of vertex data from the CPU to the GPU, which is time consuming. Especially in this case, if the slice plane changes very slightly, you can see the slice plane between these 2 cases just only move very slightly here. And what happens is that you get a completely different set of triangles when you go from this to this, which means that we might need to send like a load of geometry every single frame, which is not ideal. This is where we enter some WGPURS. WGPURS is this high-level wrapper library that's quite cool, actually. It's a wrapper around modern graphics APIs such as Vulkan and Metal. And WGPURS supports compute shaders. So we can set up the graphics pipeline like this. For each shape, we only send this vertex data to the GPU once, and the GPU is going to store it in the tetrahedron buffer. Then every single frame, all we're going to do is we're just going to send the current slice plane over to the GPU. The GPU is going to take that slice plane along with the tetrahedron buffer and pass it through a compute shader. The compute shader is going to implement the algorithm that we were just describing before and give us a list of triangles. Then we can just take this triangle list buffer and then render them normally through the normal graphics rendering pipeline and get 4D geometry run to the screen. And that's basically it. I have some demos for what this looks like. So here is a hypersphere rendered to the screen, or at least approximation of a hypersphere with tetrahedra. So this is weird because you can see the hypersphere is growing and then shrinking. I've added like an analogous 3D, like a 3D simulation, a situation here to help me explain. You can kind of think of this. Suppose this was a 3D sphere, and you had this 2D plane which was scanning across this 3D sphere, and you can see as before, you get a circle which grows from nothing and then shrinks back down to nothing. And this is kind of what's happening here. You have a 4D hypersphere, and you have a 3D plane that's scanning through it, and the sphere is, you get a 3D sphere that grows and then shrinks back down to nothing. Here's a tesseract rendered in 3D. This is kind of a boring view to it because the tesseract is actually, tesseracts are a 4D cube, by the way. This is a boring view of it because you can see that the tesseract is completely lined up with the plane. So it just looks like it pops in and then pops back out when the slice plane scans over it. But we can get like slightly weirder views of this tesseract. For example, if we tilt it on its side. So this is a more interesting view of a tesseract. We're now seeing a cuboid that grows and then shrinks back down. And if you look at the analogous 3D situation, you can kind of understand this, because if you're slicing through a cube this way, you will get a rectangle which grows out and then shrinks back down. And for like a really weird one, here's what happens if you try to slice a tesseract when it's tilted on one of its corners. You get this tetrahedron, which grows, then turns into an octahedron, and then shrinks back down to another tetrahedron, but it's upside down, and then it disappears again. This is kind of like how if you slice through a cube on its corner, you get a triangle, which grows and then turns into a hexagon and then flips upside down. But this is really hard to understand. So yeah, let's move on from this. Now we've done the basics of rendering 4D objects. So now the next thing we tackle is physics updates. All right, what do I mean by physics updates? Well, every single object is going to have a position and a velocity, and position is just where the object is, and the velocity is like how the object is going to move. So we actually need to move the object according to the velocity. We can do this using what's called simple Euler integration, which just says, well, velocity is just the change in position over time. So every single time step, we just take the previous position and then add the velocity times some delta t, which is the length of the time step to the position. And you can see here, self the position plus equals velocity times dt. We can also take care of gravity here as well. Acceleration is just change in velocity over time. So all we do is we just add the gravitational acceleration times dt. And that's it. That's basically very simple linear rigid body motion. But that's not very interesting because we really want things to be able to rotate as well. So now we need to talk about rotations in 4 dimensions. What the heck do they look like? Okay, in 2D rotations are quite simple, but like some of you might know, rotations are quite complicated even in 3 dimensions. In 2D, you can always represent the rotation with just an angle, right? But in 3D, typically what people use are objects called quaternions. Now, I'm not gonna. There's not enough time to explain exactly what quaternions are right now. But like for now, it's kind of helpful. It's quite easy. An easy way to think about them is like this: you can always describe a rotation as an axis happening around an axis. So, for example, if this cube is rotating this way, you can always draw an axis around which the object is rotating, and then there's also an angle by which the cube is rotating as well. And the quaternion is just basically a nice way of packaging these two numbers up into a way that makes sense mathematically. But if we want to talk about 4D rotations, we want a way to generalize quaternions to 4 dimensions. Unfortunately, quaternions don't generalize to 4 dimensions. So instead, we have to pull something from a field of math called geometric algebra. Let's look at how this happens in 3D. We're going to translate quaternions in 3D into what's called rotors in geometric algebra. So the way we do that is, first of all, even though I just said rotations happen around an axis, we're going to present that doesn't really happen. Where instead, rotation happens around a plane. And this is kind of the same way as looking at it, because if you think about it, if the rotation is happening around this axis, it's really the same thing as rotating this plane. And I would argue this is like a more natural way of thinking about it, because if you look at this 2D picture here, there's still rotation in this case, but where is the axis? Well, if you try to do the axis will be pointing out of the screen, which doesn't really make sense because how can it point out of the screen? It's 2 dimensions. So I would say it's more natural to think of rotation as happening around a plane. And in geometric algebra, there's an algebra to describe planes called bivectors. So if you take the dual of this normal rotation axis here, we get this rotation bivector. And as the name implies for a bivector, they kind of work like vectors, just like how vectors can have x, y, and z components here. Bivectors have components in terms of like what's called unit planes, basically. So there's 3 planes in 3D, which are xy, xz, and yz. And so this is how you would represent these structures in code. A quaternion would be a scalar plus an imaginary component, which we can represent using a vector 3. And a rotor contains a scalar plus a component which we represent using a bivector. And both the vector and the bivector have 3 numerical components. And you might think, well, these 2 objects look exactly the same. And you'd be right. They're actually mathematically the same object. And all the math for how you deal with quaternions and rotors are in fact the same. But the advantage we're talking about rotors is that rotors actually generalize in a nice way to 4 dimensions, whereas quaternions don't. So we're going to look at what 4D rotors look like. In 4D, rotors look like this. They have a scalar component, as before. They have a bivector component, which is now a 4-dimensional bivector. And 4-dimensional bivectors actually have 6 components instead of just 4, like you might think, because there are actually 6 combinations of your planes that you can make. And then there's this weird quad vector component, which is to do with double rotations, and they're really weird. And I tried drawing this diagram to explain, it's like a kind of rotation that only happens in 4 dimensions. And I don't think this diagram helped much, so let's just move on. Anyway, well, after we have that, finally, we have our physics update step. As before, the velocity is just the gravitational acceleration. We change the velocity by the gravitational acceleration. We change the position by the velocity. And then there's kind of a funny update formula for the rotation because 4D rotors are weird. This is actually the same formula as you would use for quaternions as well. And once you've added that, typically you also want to normalize the rotation as well. But yeah, once you've done that, you have rotations in 4 dimensions. So here's some demos for what that looks like. This particular shape I'm showing here is called a 120 cell. It's like the analogous shape to a dodecahedron or a D12 in 3D, except it has 120 faces. The particular face makes it look like a football, and right now it's just rotating along the XZ plane because X is pointing this way and Z is pointing this way. And it's simple. Everybody can understand that. But here's a weirder one. Here it is rotating along the XW plane. So X is still pointing this way, but W is now in a direction that I can't point to. So it's deforming really weirdly. But remember, it's not actually deforming. The shape is just rotating, and we're just seeing different parts of the shape as it comes in and out of view. And this is what I was talking about earlier with the double rotation. Because you can actually have 2 planes which are orthogonal to each other in 4D. So you can have rotations along 2 different planes at the same time, and it's really difficult to think about. So yeah, okay. But we've done the physics update, so we've tackled both physics updates and rendering. So now we get to the most complicated part of this, which is processing collisions. Because just having things move around in straight lines and rotating isn't so interesting. We also have to have things colliding and bouncing off each other. Well, how do we actually collide things? This turns out to be actually quite complicated and has a couple of steps. So first of all, we need to, every single time frame, we have to detect all the collisions that happen. Then from those collisions, we obtain a bunch of collision constraints. And then we have to solve those constraints to get updated velocity. So you can think of this as, first of all, we need to detect if any points, like any shapes are intersecting each other. And then we need to update the velocities of the objects so they're moving away from each other. So they bounce off each other, basically. So first of all, how do we detect collisions? Well, a collision really is basically if 2 objects are overlapping each other somehow. How can we do this? Well, there's an algorithm from math called separating axis theorem. And it basically says, if you have 2 convex shapes, if you can find an axis and place it next to the shapes and project both of the shapes onto that axis, and if there is any axis at all for which you can do this, and there is no overlap between the two shadows that you get, then the 2 shapes aren't intersecting. Otherwise, the minimum intersection distance here, which is the minimum distance that you have to move the shapes out of move them out of each other, will be the axis with the least overlap. I've shown the 2D case here, but this is in fact true in any number of dimensions. So the algorithm for this is quite simple. You just basically go through every single axis, project both of the shapes onto the axis, and you get 2 intervals like this. And then you have 2 cases. Either the intervals don't overlap, in which case you're done. You can just return early. There's no intersection. You already know there's no intersection because they don't overlap. Otherwise, you want to keep track of how large the overlap is, because at the end, you want to return the axis with the least amount of overlap. But there's a little bit of a problem with this algorithm, which is this for each axis part, because if you think about it, this axis could be, even in this 2D case, it could be rotated along any one of 60 degrees. So there could be an infinite number of axes to check, which is not good. So we have to cut down on the number of axes somehow. In 2D, it turns out in 2D it's actually quite simple. You only ever need to consider the normals of every single edge as the axes. In 3D, there's an additional complication, which means that you have to check some additional axes. With two cuboids, you have the minimum you have to check is 15. It turns out, and in 4D, there's a similar complication. With two hypercuboids, you have to check 48 axes. But after you've done that, you can modify the slip rotating axis theorem slightly to give us a list of contact points for each collision. This is called the collision manifold. So after you get the contact points, we have to actually resolve the collision, which is what we call it when we actually update the velocities so they move away from each other. Now, if you remember from high school physics, Newton tells us that two colliding objects will impact equal and opposite forces on each other. We don't actually deal directly with forces in physics simulations. Typically, we deal with impulses because they give slightly more stable simulations. This means for a collision, the two objects actually impulse equal and opposite impulses. And so the velocity of object A will be updated by minus the impulse, which we usually represent using this letter J here, divided by the mass. And the velocity B will be updated by plus the impulse divided by the mass. And you can see here, so A dot velocity minus equals impulse divided by the mass, and same for B. And if we just know what the impulse is here, we can just pass it to this apply impulse function, and that's it. We resolve the collision. But how do we find the impulse? Well, you have to do a bit of math. You have to plug in those two equations together, and along with an additional equation that tells you how bouncy the objects are, and we solve and we get this formula for the impulse. And we can just compute what this formula should be, compute the impulse, and then pass it to the apply impulse, and there we go. The two objects now moving away from each other, and we resolve the collision. Except I've actually hidden a lot of detail from you there, because you also have to deal with rotations and torque, but in 4 dimensions, and it gets super complicated because of 4D stuff. And finally, these are all the equations you have to mash all together to get this monster formula for what the impulse actually should look like. But after you have this formula, you can just plug the numbers in, and there we go. That's all the stuff. That's basically all the steps we need to get our physics simulation. I have some demos for the physics simulation here. Here, for example, you can see a hypersphere that's knocking down a stack of tesseracts. You can see when the tesseracts get knocked down, they rotate and then they deform, and then like some of them disappear. But remember, that's just because they're being knocked further. They're not actually deforming. They're just being knocked further into the 4th dimension, or rotating out of view. Here I have a shape called a 600 cell. This is a platonic solid in 4 dimensions. It's analogous to an icosahedron or D20 in 3D, except as the name implies, it actually has 600 sides. So you could use it as like a fair 600-sided die if you really wanted to, I guess. You can see it was almost spherical, but it's slightly bumpy, which means as it rolls around, the bumpiness makes it roll in weird directions, and it's growing and shrinking, not because it's actually growing and shrinking, it's just moving in and out of the slice from the 4th dimension. And then here's a domino track where the dominoes are going to appear to go through this solid wall. Except, as you can see, what's actually happening is that the dominoes are actually path around, so they actually go around the wall. And so we're going to see, I'm going to pick up the hypersphere here, and the object, and you can see they get knocked down because they went past the wall in the 4th dimension. This took ages to actually set up, by the way, because I kept having the problem where the dominoes were falling past each other in the 4th dimension, which is like an interesting problem to have. Anyway, and that's it for this presentation. Here I have a list of all the references which I used when I was developing this project. As you can see, it's actually quite a lot of maths and physics that I had to go through to understand, and I have the project link here. These are good starting points to learn more about some of the concepts that we discussed if you're interested. And finally, if you have any questions, don't hesitate to ask them via the Slido link here, and I'll do my best to answer them in the Q&A afterwards. Remember to address them to me. All right, thanks everyone.
Thank you very much, Tyler. Clap emojis, fire emojis, crab emojis, please. I want to see lots of clap emojis and crab emojis for that epic talk. Man, that just looked crazy. Thank you for all the work you put into doing that. Thank you. Next, we have our keynote speaker, Erich Schudt. He is the co-founder and CTO of Bippit. Clap emojis, crab emojis, and fire emojis for Erich, please, as he gets us started on a synchronous in production and how they're building their backend in Bippit. Thank you very much, Eric. Take it away.
I just noticed I was on mute, so hopefully you can hear me now, and I'll start again. Welcome to my talk on asynchronous network programming. It's a journey with Bippit. So Ernest already gave the introductions. I'll just say you can follow me on Twitter if you want to hear a bit more about our experience with Rust and the occasional tweets about the Hashi stack as well, because all of our infrastructure is built on the HashiCorp tools. So before getting started, I wanted to share this tweet by Kelsey Hightower. So the HashiCorp actually had a conference in the last 3 days. And it was a really exciting conference. If he had a talk yesterday, if you haven't seen it, I would definitely recommend that you check it out. It's not really about technology. It's more about his philosophy and experience and how he started his career. So yeah, the thing you're building, or the thing you're trying to build should be more exciting than the tools used to build it. And I'm lucky enough that actually I'm very excited about both the thing I'm building and the tools I'm using to build it. So describe what it is that we're actually building. So Bippit is a financial well-being platform. So we believe financial advice is very broken right now. If you want to speak to a financial advisor, it costs £150 an hour. And even if you can pay that amount, most will turn you away if you have less than £50,000 in your bank account. So we want to make sure everyone has access to financial advisors, because once you do, it's been shown that there is an uplift to your wealth within 10 years and a substantial uplift to your wealth. So how are we doing this? We are building a platform that connects all of your accounts and automate part of the process, the entire fact-finding process where the financial advisors have to look through all your accounts, your credit cards, and to figure out what it is that's actually happening in your life. We automate that process. And we use a provider called Trulia, which I'm sure you're all aware of, as they are hosting this right now. And by getting all that information, we can automate everything, and advisors only have to focus on the thing that they want and they love to do, which is just to advise based on all the data they have already. So that's the what. Let's get onto the how. This has been Bippit's journey in the last year and a half or so. So 2018, I was experimenting with Rust. And then in 2019, we had our first production service in Rust. This was within Q1. We very soon realized if you want to integrate with external services, Rust doesn't have a lot of SDKs. And as such, we have to bring a second language just to build things a little bit faster. So we built 2 services in production using Java, which we didn't intend to, but that's what you have to do with a language that is quite young at the time and in the ecosystem. In Q3, we included Risotto crates, which is a really great crate if you're using anything with AWS. Whether it's the RDS, SNS, SQS, whatever it is, you can use that crate to connect to it. And then in Q4, as you can imagine, we were very excited about async await. It made all of our code a lot easier to write, a lot easier to read. It's just the refactoring took a bit of effort, but it was great once it was all done. And then we brought in BB8 for database connection pooling. I'll discuss that a bit more later on, but as you can see, measuring the code coverage itself came almost a year after. And this is another thing that we noticed with Rust. There isn't a lot of tooling available to get some of the things that you want to get done quickly. We only wanted to build and use crates that are unstable. And a lot of things that deal with code coverage weren't in stable Rust at the time. Right now, we have over 10 services in Rust in production. And in the future, we are looking at mainly the async trait refactoring. So one of the things that you can't do right now with async awaits is have traits. There is a workaround using an async trait crate, but it's not very nice. And I'll get to the details of that later on. Another thing we'll look to as well is machine learning with Rust. And if that's something you're interested as well, you can join the Are We Learning website and just have a look there. It tells you about what's available, what's not, if it's the right time to use it or not. So there are so many things that we worked on in Bippit with Rust in the last year. So why focus on network calls? So one of the reasons we picked Rust is because we wanted to make sure our servers were as fast as possible. And Rust gives you not only these reliable services with the inbuilt error handling and everything else, but the fact that you can make asynchronous calls as easily as possible helps to build these very, very quick APIs. So let's just start at the very beginning. Do you actually need to make network calls? If you think back to these LAMP servers at the very beginning, you have your application server and your database within the same server. You do have to make a network call, but it's on the loopback interface. So it's actually quite fast and it's negligible. This is probably something that is more familiar, especially in production. So you have an application server on a separate server, and then your database on a separate server as well. And this is usually on a cloud, and it's usually on a high availability configuration. So whether it's a cluster of databases or a read-only replica as well. And it doesn't just have to be databases. It could be anything from a queuing system to just an alerting system. It could be anything at all. You still have to make those network calls to communicate with it. What's becoming even more common these days is this microservice architecture. So you have a lot of different services running on multiple servers. And as you can see, the more you have and the more they interact with each other, the more of these calls they have to make, the more they have to wait for the external service or the other microservice to do some processing and then respond. This is a smaller example. You can imagine it could spread out to a lot more services. If you imagine, say, Monzo, for instance, they have so many of them. But it's good to maybe discuss the first, if you're looking to get as much performance as possible, the network calls isn't the first thing to look at. You can look at a database, your queries, you can look at your architecture, which is probably where you get the most gains. If these services are solely dependent on each other and always has to make calls to another one, then perhaps you need to think about combining them or just think about the design of it. Just assuming everything else has been done and you still want to get the most performance services as you can, then you start looking at, okay, what can I do about these calls I'm making to not just my services, but to all these external services that I need to use. So we can bring up one of these application servers that I've been floating around in previous slides. And what do we have in it as a service in Bippit? First, we use Tokyo, which is an executor in order to run these asynchronous codes. At the time, Tokyo was the standard. There wasn't really much competition. And a lot of tools that we wanted to use was built on top of Tokyo. So it was just an easy decision to make. But right now, async standard is a good competitor. So I think you can have a look at both to see which ones you want to use. In terms of the HTTP server, we ended up using Hyper. So most people ask me, why Hyper? Why not something more of a framework, something easier to use? So we did have a look at a couple of them, Rocket, Iron, a few others. And we noticed most of them were built on top of Hyper. And looking through the code, it seems quite similar. At the time, they were very similar. And even more importantly for us, because we wanted to build very performant APIs, we wanted to make sure we have access to the async code levels as soon as possible. So it made sense for us to go with Hyper at the time. And all of our service right now is built on Hyper. BB8. So keeping with our goal of having very fast performant service, we wanted to make sure we had connection pooling. So before that, all of our database connections, we would create a connection, make a request, get a response, and close the connection, which was very inefficient. By including BB8, you can have a pool of open connections. You use one, and then you use it and put it back in the pool without closing it. Before BB8, there's a crate called R2D2. Hope you see that reference over there. So R2D2 didn't support async. It was just for synchronous Rust. And this crate was created to help with asynchronous code. And for our database crates, we use Tokyo Postgres. And it's similar to the previous two. We wanted to make sure everything we use has async features in it. Diesel is probably the most popular, especially at the time, that crate that people use to connect to their databases. But they had no support for async at all. Maybe they do right now. I haven't looked in quite some time. And finally, Risotto, which I mentioned as well, which also supports async with connecting to Amazon services. You can see a pattern here. Every crate that we use needs to support async because we want to make sure we can always use that code when needed. And just to close off what else is on our application servers, just mention quickly Serde for JSON serialization and deserialization, and then slog for structured logging, and also tracing, a hacky way of doing tracing. So this is what a client looked like before async await. I wouldn't spend too much detail just looking into this, but just to highlight how messy it was, you can have a lot of nested code. And if you have conditions in there, you have quite a lot of these either A, either B calls in between. You have to actually downgrade your Rust and your crates in order to have this code working and running, which I didn't want to do. So I just wrote this. Probably doesn't compile, but as you can see, it was really, really hard to write asynchronous code before async await. And then, yeah, Rust 1.39 came along and it made things a lot easier. This is what it looks like now with async await. A lot cleaner, a lot nicer. You can easily read and write this. So I'll be using this client for the next set of slides just to explore making these calls within your service. I have to mention there's a slight modification on this client that was used here. So it's not just returning. I'll just go back and explain the code very quickly. So it makes a call to an API, one of Bippit's APIs, to get the version of the API. It creates a request and then creates an HTTPS client, sends that request, parses the response, and then returns a string back to the caller. So this was modified very slightly to time it as well. So at the beginning, it starts the timer. At the end, it stops the timer and returns both the results and the duration of the call. So here's an example where we're making one call using the get version function that we looked at previously. To explain how this program works, it does almost the exact same thing I said before. So it starts a timer, and at the end, it prints out the duration of this program. And right before that, it also prints out the results of this get version call plus the duration of that get version call. So I run it already in the background and got the results. This is what's printing out. So it got the version 2.2.4, and it took 170 milliseconds to do. The duration of this program took 170 milliseconds as well, which is expected. So now we make 3 calls just to see what it looks like. You're making 3 same calls to the exact same clients that we looked at. And then we're getting the duration and result for each one of those 3. And at the end, we're printing out the result for each one of the 3 calls and also the duration for all 3 calls. So if you're to guess how long this program would take, what would it be? If you're thinking 3 times more than the previous one, then you're exactly right. And you have done some work with async awaits already. So it does this synchronously. Although everything here is written with async, the code is actually run asynchronously. So the first one took 177 milliseconds, second one 134, third one 118, and the 430 for the entire program is pretty much a sum of all of that. So how do we make sure we can run this asynchronously when we need to make sure we are getting data that we need and then processing other data in case we don't depend on it immediately. So we can let it run in the background, do something else, and then put it all together at the end. And this is what it looks like. There's not much difference between the two. You just have to create a vector that holds the 3 calls that we created from the get version. This vector stores the futures of the function, meaning they haven't been run just yet. It just stores the code that will run once you have called it to run. And by calling the join all function, it runs all of these 3 at the same time. So like before, we get the duration and the results for every single one of these 3 calls. And at the end, we print it out again. And that's what's printing out. So all 3 got the version correctly. The first one took 186 milliseconds, second 178, third 190. But the duration of the entire program is pretty much equal to the duration of the longest running function, which is 191, 1 extra millisecond just to close it off. So this shows all 3 calls were done at the same time in parallel, brought together, and then resulted in substantially reducing the amount of time that this program actually takes. So what's so unique about this? A lot of other programs have this as well. But the way Rust does it does have some uniqueness, which I'll go through now. So one, it's very robust. And this comes from Rust's own language itself. with the error handling, the matching of every arm, etc. So it's very unlikely that you have an error there once the compiler is happy with it. And two, which is probably the most important part of it, it's zero cost. So once you create these threads, they're green threads, meaning they're not managed by the OS, but it's managed by the executor, in this case, Tokyo. And for the threads and the function that they run, they are compiled to the equivalent of state machines, meaning they're pretty much very, very long enums. So once it actually gets to running the code, everything is already ready and it just runs it very quickly. If you have a very, very long running async function, or you've written some HTTP server that's completely async, you probably come across max limit type reached. And that's exactly what this means. So all the different conditions, all the different loops and the different async functions creates a very long type. And if it reads that max, you just have to keep extending it. And the third part of it, which is also a big part, is that it's very, very easy to write asynchronous code. It's almost as easy, or just as easy actually, as writing synchronous code. So this 2 lines is the only changes I made to make this run in parallel. So what does this mean? Well, to me personally, this pretty much means that once you want to write asynchronous code, it's super easy. And that's what I understand every time I see the term fearless concurrency in Rust. So every time you're in a project and you hear this sometimes, keep things very, very simple, keep it on one thread, and it's easier, it's safer, and all of that. Well, you can point them back and say, actually, in Rust, it's pretty much the same thing. There's not much difference between the two at all. Plus, you get all the performance benefits. So what are some takeaways here? One, your API is as fast as the amount of time spent on IO task. And this is assuming you've done all your database, query enhancements, and all of your architecture is solid as well. And two, using spawning and combinators, time on IO can be greatly reduced. So the example I showed with join all, that's one of the combinators. There's a couple of them. You can use select, which runs multiple async functions and then just returns the fastest completed ones. You could use indents, which just runs them synchronously, but then you can chain them together to make them a longer async function. And there's a lot of them that makes working with concurrent programs a lot easier. And spawning pretty much just gives off a function or a piece of logic to a separate thread to just run and then complete on its own. And with async quick, it's really, I can't stress this enough. It's really, really easy to write concurrent programs. And I would completely recommend putting this in your network calls, especially, whether it's to your database or to other services, because that's where you're just waiting on something to happen and where you can spend a lot of time doing other stuff. So in our year of working with Rust, what has worked well? It's been very, very fun to build. I think this shouldn't be a surprise. Rust has been voted the most loved language for the last couple of years. We're seeing less errors. So we actually put all errors that we see in our logs into our Slack channel. And other projects, you would probably spend every second looking at that channel. But with this, it's actually very manageable. There's very, very few errors happening. You have very, very fast APIs, and it uses a lot of less resources, which means reduced server costs. Just on the resources point, if you recognize this is an example configuration file for a Nomad job. This is an example production service that we have. So it's just running on 64 megabytes, and it's fast enough to serve everything that we need that the service is actually providing. And what didn't work so well? Well, the lack of SDKs was one of the major factors that we found very, very quickly. We integrate with Firebase, and there's no SDK to integrate with them. We first started just integrating with the APIs, and then once there's authentication involved, then you need to start getting into cracking tokens, and even the token crates aren't very mature. So it just made sense to write that piece in Java. Another part of it is the lack of options for tooling, and this came up for the measuring of the code coverage. It took us quite a while to find the right tool to do this, just because we wanted to make sure everything was on stable Rust and not on nightly Rust, and the amount of time to become proficient. Hopefully it's past that phase now, because with async arrays, it's actually very easy to read code and understand code. So hopefully that goes down a bit. For us, the async await and the major refactoring was quite painful. So was it worth building the entire system in Rust? It's a massive thumbs up from us. Yes, we thoroughly enjoyed it, and we're seeing the benefits by looking through our logs, our services, our durations, our latencies, everything. Thank you. And here is the link to Slido as well. If you have any questions, you can put it in there. And if you want them directed at me, you can just mention that as well, and I will answer them.
Thank you very much, Eric. Clap emojis, please. Crab emojis, fire emojis. Thank you very much to our keynote speaker. This just kind of shows why us Rust stations are such async await nuts. We're so crazy over async await. You've just shown us all of the great benefits and how that's really helped you directly in a production setting as well. So thank you very much for that insightful talk. Now, just a couple of reminders of the announcements that were made. So we're going to the Discord channel after this meetup for some after meetup drinks, virtual drinks afterwards. And also, please remember Rusty Days. The Rusty Days conference is going to be where the Rust London meetup will be next month. We're not going to have a Rust London meetup here. Everyone should go to Rusty Days because that's where it's going to be. All right. Now, just want to welcome our last speaker who's going to close us out, Alec Mocatta. He's a long-standing member of the London community. He's been there since the good old days, and he's going to be giving us his talk. So please, lots of crab emojis, lots of fire emojis, lots of clapping emojis for Alec. Thank you very much. Take it away, please.
Well, thank you very much, Ernest, and thank you to our other presenters. I really enjoyed both of those talks. So I'm going to talk today about data processing in straightforward idiomatic Rust. Specifically, I'm going to talk about my journey building up from Rust iterators, which I found to be one of the highlights of Rust, one of my standout favorite features of Rust right from day one. We're going to take a whistle-stop tour, building up to a vision for data processing in straightforward idiomatic Rust. And so this is the journey I went, starting there, trying to get to what I'd experienced in other languages like Python, the kind of productivity and the kind of power that I'd seen there, but in Rust. So we're going to go through a journey. Our goal here, we're going to imagine we host a website and we want to calculate some metrics from the web access logs. We want to run it in parallel. We want to take full advantage of our computer, of our expensive desktop computer. And we want it to be really simple, really simple. We want to have essentially zero boilerplate, as absolutely minimal as it can possibly be. So we're going to start with an example, and this compiles, and this was how I would probably do this in straightforward Rust. If I just had to do a simple task of reading a CSV and building up essentially a histogram of when in the day traffic arrives at my site from my access logs. And this is this is pretty straightforward. We're using here, Eric already mentioned the crate serde. That is, the CSV crate is passing records. We're then inserting them into this hash map. We're rounding to the nearest 15 minutes such that we can then build a histogram out of it. And we're then sorting this histogram and printing it out. And so the result here, what you would see printed would be for each 15 minutes of the day, how much traffic you get in that time span. So this is the example we're going to be working with. I'm going to each slide, I'm going to add something to this that makes it a little bit more powerful and a little bit easier to use, I think. So the first step is introducing typing. So on that first slide, we were dynamically typed. What that means is that we don't need to specify exactly what the type is in our code. But if we get it wrong, if we try to use the data in the wrong way, we'll get runtime crashes. static typing, as you can see, we're describing what our data looks like here. We're describing the row structure. And what that means is that we can then work with that. We can work with it in an easier way. We don't need to bother kind of interpreting something and passing it as an IP address. We already have it formatted as an IP address. We can work with it in the way it's designed to work. So, for example, naive date time is a struct from the crate. There's a crate called chrono, and once it's typed like that, you can do all kinds of stuff with it. You can take the time, you can take the day, you can shift it, you can truncate it, etc. The other upside is that this is probably quite a bit faster. It depends what scale you're working at. But if you start deserializing a large enough set of data, even something as simple as sort of CSV rows, it's doing a lot of allocation and deallocation behind the scenes if you're doing it dynamically typed. And that ends up being a bottleneck, and I've seen this. Static typing does away with a lot of that, or as much as you can get away with a lot of that allocation. So rather than there being sort of a vector of 4 strings, we've got just sort of 2 allocations here, one for string and one for URL. That brings me on to gradual data typing, which for me is is something I've really enjoyed with Rust. I think the Serde JSON crate, if anyone's familiar with that, does this really, really well. I don't know if you've used this, but there's this enum called value, which can represent any valid JSON type. And what that gives you is the option. You can either specify the type statically using structs, as we had on our previous slide, or you can mix and match that with this enum that can represent anything. And you can even combine them. So you can have a struct with the value inside it. If, for example, you have a payload that is of various different types, you don't necessarily know statically, you don't know at compile time what that type is, you can include value in the struct. And for me, I found that really, really useful, and something that I hadn't seen in other languages. And here's a quick overview. And one of the upsides, of course, gradual typing, being able to include static types when you know them. I mentioned a performance boost. Well, I actually measured this with the Apache Arrow Rust Parquet implementation, and I found it sped things up from about 1.5x, where there was minimal allocation, to 17 times speed up, where it was doing tons of allocation. So that's quite a sizable speed up just by introducing types. So our first couple of slides, we were manually creating a hash map, and we're inserting stuff into that using functionality that, as Rust programmers, we probably know, but maybe if you're more of a data science focused, you're not going to be familiar with those things. What you want is the library to do this kind of thing for you. And that's what we're doing on this slide. We've introduced this histogram, what's known as a reducer. So it's something that goes, something that you can call on an iterator, and it'll do something. In this instance, it's going to give us the histogram that we wanted. And so it saves some lines of code of setting up a hash map and inserting into a hash map. And fewer lines of code means hopefully fewer space for there to be bugs, a fewer space for us to make mistakes, and less experience required. Anyone can write .histogram, whereas inserting into a hash map is potentially a little bit outside of some people's area of expertise. So then the question arises, you have one of these reducers at the end. What if your data set is really huge and you don't want to iterate over it multiple times? Let's say it's sort of, I don't know, many gigabytes, and iterating over it takes a minute. What if you want to do more than one thing? What if you want to get a histogram, but also some other stat? Well, I've seen some kind of attempts at this, but I've had my own attempts at this, and this is what it looks like. So what's going on here is a new iterator adapter, an iterator reducer that I've called fork. And what it does, it lets you essentially pipe what's coming out of an iterator into multiple reducers. These reducers, you can create them by writing identity, which just means sort of start the iterator adapter chain. and then iterated transformations as you would normally. .map, we're again truncating it, and we're creating a histogram. And that, but we're also, as well as that histogram, we're also counting the number of hits to our homepage, for example. And so fork becomes quite powerful. Suddenly it means rather than having to iterate over the dataset multiple times just to get a histogram to get the count, you can actually combine as many different things as you want in one pipeline, essentially. But that raises the issue: what if this starts to get a little bit unwieldy to read, a little bit unwieldy to work with? What can you do about that? Can you decompose this? Can you define parts of your pipeline and then sort of plumb them together? Well, yes, you can. You can define this method pipe that simply takes two pipelines. Again, they're defined. Start with identity dot filter, whatever, and you can then join them together. .pipe just literally fuses them together. And then again, we're taking our iterator and we're piping it into the reducers that we've defined here. And these are all quite sort of simple examples, but when you're dealing with more complex pipelines, this becomes really useful. The next step is once you start to do this in production, what if you want to run a bunch of different computations concurrently? So Eric did a really good job talking about async await. So you guys know the gist of it. So I'm just going to highlight here again, Tokyo main. This is essentially saying that we're using the Tokyo runtime that Eric mentioned. And other than that, there's essentially two changes, very simple changes to our program. One is we're using the async keyword because this is an asynchronous function. And the other is .await. And what that does is it asynchronously waits for the task to complete, and it lets other tasks that might be running, it lets them continue to run. We're not blocking any tasks from running when we call .await. And suddenly now this example is asynchronous, and these iterators are now streams. Streams are sort of asynchronous iterators. And what this means, we could be streaming data in from like servers, S3 servers, somewhere where there may be some latency, and it means we can do a bunch of those operations at the same time. And a little bit of an overview, and this has been covered, an overview of async. So what I have gained from async is being able to think of threads as being unbelievably lightweight. So previously, there's nothing stopping you from spawning up loads of operating system threads and kind of achieving most of the same kind of upsides of being able to just run a load of concurrent stuff. But OS threads do have some weight to them. If you start spawning thousands of threads, everything will suffer. Everything will start to grind to a halt. Whereas the tasks that are sort of part of async await, you can think of as being essentially unbelievably lightweight. And so you can spawn thousands, tens of thousands, essentially as many as you want. And you don't see the same issues that you see with OS threads. Again, it requires a runtime. There are two primary ones, Tokyo and async std or async standard. As Eric said, Tokyo has far wider ecosystem adoption. And that's it. There are two sides to this. If you're playing around and you're not interfacing with libraries like Risotto and Hyper, then async std is worth trying out, because in my opinion it's better designed. It's easier to get to grips with, in my opinion. But as it stands, Tokyo is the one that's adopted by most of the major ecosystem crates. One downside of async that I've observed is that compile times take a hit. In my experience with the project I'm working on, it actually was a really significant hit, and I'm hoping I can mitigate that. But I know that a lot of work is going into the compiler to make this better. And there is a reason for this. It's the compiler has a harder job to do. As Eric said, it's compiling this nice, neat code down into very complex state machines. And that's not an easy job. So there's a reason behind it. So the next thing we want to introduce is really taking advantage of our machine with 18 cores, or however many it's got. And we're introducing essentially one thing here. We're introducing a thread pool. A thread pool is how, maybe you're familiar with this library Rayon. It's a fantastic Rust library that is very similar. You create a thread pool and you can then sort of spawn out work to it that runs in parallel, and you get the result. We're doing that here. And the none parameter we're passing is essentially just meaning the default parameters. So the default level of concurrency, which is of the order of sort of 100 jobs per core, 100 tasks per core at a time. We're then passing that pool to our reducer, to this histogram reducer, such that it can then farm out work to that thread pool. This is what that looks like. This is an architecture that fits this sort of iterator stream model we're talking about. So some data is defined. It can then be broadcast out, sent out to first of all a bunch of different threads, and then within the thread it can run a bunch of different Tokyo tasks. And these Tokyo tasks will run it run this concurrently. Our machine will run a bunch of these threads concurrently, and then as work is being done, it's reduced, and so the results of any of this work is kind of combined however we define it to be combined, and combined again, and the final reduced step, that's then the result that's returned to us. So to go through our example, the data are web access logs. That data is what's being broadcast, or even sort of where that data is sitting. Perhaps if it's sitting on a bunch of S3 bucket, on an S3 bucket, those different files, those are what's being broadcast. And then the Tokyo task would be reading that data in, reading in its partition, processing it anyway in whatever way, whether that's building the hash map of the histogram, and the reduce will be combining those histograms, and the final reduce will be combining all of the histograms into the one that is returned to the user. So what does Rust give us to enable data race freedom? So data race freedom is something that it's almost like it's kind of hygiene in Rust. If all good Rust crates avoid data races, because Rust makes it possible to do that, which is fantastic. And not many other kind of languages that give you the control that Rust gives you have managed to achieve this. So fearless concurrency for me is more about being able to use multiple threads on a machine, being able to use multiple threads and have them do work, and then be able to kind of take into account this work, bring this work together, reduce it in some way, and at no stage expose yourself to the potential of data races. And Rust does that with this idea, with essentially kind of two ideas. First of all, ownership, combined with these two traits, send and sync. So everything in Rust, everything has an owner, and the send trait, if a type implements send, it means that it is safe to send that type to another thread, to transfer ownership to another thread. If it implements the sync trait, that means that it is safe for that type to be accessed, to have shared access across a bunch of multiple threads. And these are really powerful. You can build fantastic abstractions given the idea of ownership plus send and sync. And it means that we can kind of create super powerful libraries where we just don't need to worry. We can do things that are almost reckless in other languages, but in Rust we know it's safe. That brings us on to what I see as the kind of the final piece in the puzzle for data productivity, which is being able to kind of abstract over data source. So we can simply kind of plug and play different data sources. And you can see here there's a trait here. I've named it source, which is, in this example, is abstracted over various data sources, including the example given here, which is sort of a partition Parquet file sitting on S3. So this is a directory on S3 full of a load of Parquet files. And we can simply write that and use that as the source for this daily traffic computation. If things changed, let's say we wanted to our logs switch to, I don't know, Azure blob storage, we could do that. And we wouldn't need to change our daily traffic function because it's generic over where the data is coming from. All the daily traffic function asks for is just a source of rows, the struct we defined earlier. And that brings me on to the library that I've kind of has come out of my working on this, which is I've called Amadeus. And essentially the point of this slide is that this is what everything has kind of been building up to. Everything that I've mentioned so far is an ingredient in Amadeus to try and solve the issue I outlined initially. I'm trying to be productive with data science in Rust, in as close to idiomatic Rust as possible, where you have the power of something like iterators with superpowers, and you have async await, and you have these nice built-in data functions, like for example, finding a histogram. Now, these are some of the points about Amadeus. It's got a bunch of connectors: CSV, JSON, Parquet, Postgres, CloudFront logs on S3, and more. It's got some data science primitives. It could do with a lot more. There are a lot of data science primitives that exist, but I'm working on that, and any contributions enormously welcome. It is of course asynchronous, and it uses Tokyo as its runtime. So you can run a bunch of these different jobs at the same time. It's also pretty fast thanks to how it does typing. The one kind of bonus thing that I wanted to also mention is that it also runs distributed across multiple servers. So again, we're just going to quickly highlight the sort of changes on this slide. There's essentially really three changes, even some of them are fairly minimal. Three changes. First of all, we're using a process pool. Again, we're just using default arguments, but just for this kind of sake of thoroughness. And these arguments serve the number of processes to have in the process pool. We're just going to use the default. The number of tasks to have per process, and then each process, how much CPU and memory we should allocate to it. Because when you're distributing to a cluster, that is important. You need to know how much memory is in use where. The other changes are simply just changing par stream, short for parallel stream, to dist stream, short for distributed stream. And then this other thing here, and this is the one that's slightly odd. We're using this interesting macro here, fun exclamation marks. This is just a Rust macro. It's a Rust procedural macro. And what it does is it just makes closures serializable and deserializable. And this is how we can define work. We can define map functions and filter and whatever else that can be farmed out to a process pool. And farming it out it involves sending it over the network. Sending it over the network necessitates serializing and deserializing. And so that's what this fun macro does. It makes our closure serializable. And this is then what that process looks like. And it's like the previous diagram, but just another layer. Our initial broadcast is broadcasting out to multiple processes. Then within a process, it's being broadcast out to multiple threads. Then a thread is being broadcast out to multiple tasks. And again, for the reduced stage. And this is this is working today. The library is it's pretty bare bones, and there's a lot more I want to do with it. But this works. And it works because it's using another library that I wrote called Constellation. And this is the goal of Constellation is to try and make distributed computing as easy as parallel computing, by giving you the same kind of parallel abstractions you use, like spawning a thread and channels, by making those available for processes. So you can spawn a closure that will then run maybe on the same machine, but maybe somewhere else in the cluster, depending on where there are resources. And you can simply have a channel. You can send and receive over a channel to it. The Constellation makes this library a lot easier to implement. Otherwise, you need to think about kind of running this kind of Amadeus stack on each computer, and that's overhead. I want to have a cluster and then just run my program, and it to automatically to be able to like essentially have one program that this program runs on a cluster rather than just running it on a machine. And that is the end of my presentation. I hope you guys have enjoyed it. And this is my this is my call to action. I'd love if anyone dropped by and maybe said hi on the chat, or maybe gave a star on the repo. I wanted to have this ready for today, but unfortunately I don't quite. I'm working on something really cool that will bring in a really interesting kind of group by operator to Amadeus. And so that will be dropping in about a week's time. So that's a reason to drop a star on the repo. Anyway, thank you very much. Any questions, please do feel free to ask on Slido. We'll be here. We'll also be on the Discord, or at least I will be on the Discord if there are any questions thereafter. And thank you very much. I will hand back to Ernest.
Thank you very much, Alec. Clap emojis, crab emojis, fire emojis, please. That was an amazing talk. Thank you very much. Alec, could I just ask you to put your last slide back up again, just to showcase the Amadeus community?
Is it up?
No, if you just want to share your screen again.
Yes, there we go.
Here we go. So please, please, please join the Amadeus community. They've got lots of amazing stuff going on, like Alec has just described. Like he said, please star his GitHub repo, follow him on GitHub, and let's continue to build the Amadeus community and everything that Alec has got going on. So here's the links to it. Please, please, please check out the Amadeus community and everything that they've got going on. Thank you very much for that, Alec.
Thank you so much. Thank you for the plug. You're making me blush.
No worries, dude. You put in a lot of work. So really, really cool stuff. Now, we're going to have our panel session where all of the questions that have been collated throughout the entire meetup get asked directly to the speakers. We have TrueLayer, who are hosting us through Slido, who are going to present the questions, and we're going to get started with the top rated question. What's the question at the top? Big thank you to TrueLayer, by the way, who have always been our amazing hosts throughout this year and last year, and have done so much for us. They continue to sponsor, they continue to help hosting and supporting the Rust community in London. So big thank you to TrueLayer for all of that. They're also hiring as well, so if you want an actual Rust backend role, please check out TrueLayer. They've got real Rust backend roles available for anyone who wants to work with them. Right, first question from Peter. Hey Peter, how's it going? This is to Tyler. Awesome presentation. How did you debug problems when your visualization didn't surf problems, like in the falling dominoes example?
Hey, Peter, thanks for the question. Unfortunately, I don't actually have a very good answer for this because like I don't know if there is really any good method for doing this, especially because it's 4-dimensional. It turns out the visualization is actually quite nice for detecting when like things have gone wrong, because you can scrub through the w-axis very slowly, and then you can see if things are intersecting when they shouldn't be. But other than that, it was a lot of stepping through the debugger and staring at tables and tables of numbers and trying to figure out which one was wrong. I'm not. I could. I like at the time. I just thought that was the easiest thing to do, and like it's not so easy. So yeah, I'm sorry. I don't have like a great answer for that.
No worries. Well, you you certainly did, give a good answer as well as you could do. So thank you for that, Tyler. Thank you. And another regular, Ricardo. Hey, Ricardo. Another question to you, Tyler. First of all, Ricardo's first question is to Tyler. Were there any advantages you found by using Rust for a physics simulator, be it performance, libraries, ease, or something else?
So yeah, with choosing Rust, because really the code is kind of agnostic. You could write it in anything apart from like my use of WGPURS. But with Rust, what I found is that when you are doing a lot of mathsy and physicsy code, you want to be able to write things in like you want to be able to write most of like raw multiplications. You want to write like essentially Python-like sort of things where you just take vectors and matrices, mash them together, and do that sort of thing. And Rust is great at that because of its type inference. So you can do things where you just use like star for multiplication and whatever. But Rust will warn you if you're doing something stupid, like you're trying to pass a like in my example, it would be like if you're trying to like left contract the bivector with like a trivector or something weird like that. But like if you're trying to use a vector and a matrix, but they're the wrong dimensions, and that's that like helped fix like catch a lot of bugs where Rust just wouldn't compile if the dimensions of your matrices are wrong.
Cool. Thank you. Thank you very much for that answer. Next question is to Alec, and it's from Avi. Have you compared performance to Apache Spark? Oh, really good question. Do you support cluster-wide computations? And that's to Alec.
Thank you, Avi, for the question. So I have not yet done a head-to-head, but I have used Spark in the past. And I mean, this is from probably about 3 or 4 years ago when I last used Spark. In my opinion, Amadeus will be substantially faster for what Amadeus does. Spark has a lot more features. Spark, of course, has had many man years more effort put into making it featureful. And also it provides this idea of a kind of like a data frame or data set or whatever they call it now. So that's a more that's a high level abstraction than what Amadeus currently operates at. But for what Amadeus does, I would expect Amadeus to be almost essentially as fast as it's sort of theoretically possible to be, because all these abstractions I talked about are essentially zero cost. I mean, that phrase needs sort of more rigorous defining. But these different parts of the pipeline I was talking about, there's no memory allocation in those. Even fork, there's no memory allocation. So there's nowhere for performance to kind of be eaten up, as it were. So I would expect it to be 1 or 2 orders of magnitude faster than Spark for serious computation.
Thank you very much for that answer, Alec. Next question is to Erich. Why did you choose HTTP for your microservice RPC instead of something like Thrift or gRPC? Ooh, the Golang guys.
Yeah, that's a very good question, and I struggled with that decision for quite some time. But I think ultimately the goal was to try and be as fast as possible. I know there are ways where you can interface an HTTP call into a gPRC or an RPC client, and there are ways you can do that the other way as well. But we just wanted to build everything with one protocol, and then once we see that if we need a different one for different reasons, mostly for performance reasons, then we will switch. But because we have to already build things in HTTP to interface with things like TrueLayers APIs, it made sense to just stick with HTTP throughout and then look to change it when we need to.
Cool. Thank you very much for that answer. Another question from Peter. What are your SLOs for the service? How many QPs, or is that QPS? Is 95 to 99, and max response latency. So we want to get some metrics now.
Yeah, these are tricky to get. So the objective right now is to make sure our latencies are always less than a second. But then there are parts of the system and the services that interface with the bank, so users' bank accounts. There's not much we can do there at all. Sometimes those requests take like 10 seconds even. And there's nothing to do with TrueLayer either. So TrueLayer needs to go to these banks, and then they can be very slow. So if you're looking at the latencies for the entire service, then it is very, very high. And there's not much we can do about there. But we are looking to redesign a lot of our services in a way that it doesn't have to make those live requests to the banks. They just rely on their cache data for as much as possible. And then only if those cache are invalidated, we will go and make another live request. Once those are done, we expect to definitely hit below, I would say 500 milliseconds would be a really nice objective, but I think keeping it under a second is what we'll be aiming for.
Great, thank you very much. And when you're ready to share any more benchmarks or anything like that, please feel free. Another question from Peter to Alec. If Constellation abstracts the cluster away from standard thread spawn and others, where do you configure your cluster? Is it on-prem friendly?
Thank you, Peter. Yeah, it is on-prem friendly. I mean, my testing has been on the cloud, but spinning up my own instances, not currently using Kubernetes, although it does have a Kubernetes backend. The way that Constellation works is you start it running on a bunch of servers, just start a process called Constellation running on a bunch of servers. And then on one kind of head server, one chief server, you simply list the IP addresses and the ports and in a config file, and then run Constellation on that. And there you have your cluster. You can then just deploy to it from the command line. It's literally just you kind of cargo deploy the IP address of the chief server, and your program will then run on the cluster.
Cool. Thank you very much for that answer. Another question to you, Alec, from Lau. You said you make a thread pool that you use with Tokyo. I don't know much about Tokyo in async, but doesn't it have its own thread pool?
Yes, you're spot on. It does. And the reason why Amadeus has a sort of a type called thread pool is for essentially that you have to be able to pass some config that describes the concurrency that you'll permit at any one time. And the reason why that's important is because otherwise you might have essentially, so let's say you've got, I don't know, 100,000 tasks you want to compute, but you've only got enough memory to compute a sort of 1,000 at any one time. If you don't enforce that concurrency limit, then all 100,000 will be submitted to Tokyo, because Tokyo won't apply that back pressure, and you'll run out of memory. So you're right. Amadeus uses the Tokyo thread pool, but it does apply that limit to it.
Thank you very much. Question to Tyler, and it's kind of a follow-on from the first question that you were asked by Peter, is what tools did you actually find useful for debugging and navigating your code?
Yeah, so for debugging, I just use Rust Analyzer. So Rust Analyzer is a nice plugin. It has a hook onto LLDB, which conveniently works on, it works pretty well on Windows. I was surprised at how well it works, but it does leave it is still a work in progress. But when something would go wrong, it would just be a lot of me stepping through with LLDB, the code, inspecting the numbers, does it still make sense, and then trying to bisect where the actual issue is. All right.
Yeah, great. Thank you very much. And were there any other tools or plugins that you used?
For debug, well, apart from that, you also had like, good old print statement debugging where you just use the debug macro over and over again. But no, not for something as niche as this. I didn't find any good. Oh, sorry. For graphical issues, I did use RenderDoc because RenderDoc hooks into like you can hook. It supports OpenGL, it supports Vulkan, and it can just hook into the graphics pipeline. You can take a trace of all the things that are happening in that frame, and so you can tell, hey, there is a shader step here that's messed up, and that was really useful when I was debugging graphical issues.
Cool. Great, thank you very much for that. So the next question from Mike, because it's not addressed to anyone directly and it's an async question, I'm gonna ask this to both Eric and Alec in both of their contexts. So Mike said, have you found any performance degradation since switching to async await with Rusto?
I can maybe start off. Risotto, which is a craze.
Risotto, sorry.
Yeah.
I couldn't read that. Thank you.
So we've definitely seen much longer compilation times, which Alec mentioned, since we switched everything to async await. But in terms of the overall performance, we've seen it gone down actually. So it is a lot faster since everything has been moved to async await. But I should mention that we aren't instrumenting every single part of our service at the moment. So we just know from the very start to the end, is it faster? And the answer is yes. But whether the async calls to Risotto actually made the difference, that I can't answer right now. But once we start inserting a lot of instrumentation, then I'll be more confident about which parts of the systems are actually performing very well.
And I don't have too much to add, but just one thing that I've observed anecdotally is that actually increased memory usage after the switch to async await, I've noticed. I think the reason for that is that you're essentially, oftentimes you have to box futures because let's say you're returning them from a trait method. And in that instance, that what you're boxing is a struct that's essentially been kind of created by or an enum that's been created by the compiler. And the compiler yet isn't as good as it could be. And so oftentimes that enum that's being boxed and put on the heap could actually be quite a bit larger than it actually needs. So I think that's why.
Yeah, and just to add on that as well. So that's something we noticed also once we started boxing a lot of different things. Usually the database calls and also initially with Risotto as well. So we built everything without having to use a single box. That took quite a long time. But after doing it, yeah, we did see the memory go a lot lower.
Amazing. Thank you very much. And thank you all for your very insightful, very clear answers. The last question from Alex. Yes, the presentation will still be online. I will share them in the Discord room when we leave here, when this is over. They'll also be uploaded to the Rust London YouTube channel. So if you go to Rust London, or if you type in Rust London into YouTube, you will see the videos from last month and this video uploaded on it in the next couple of days. What I'll also be doing is I will be uploading some of the archive that we have from last year's Rust London talks as well. Because July, we're not going to be having a formal meetup, a formal London talks like this, because everything's going to be happening at Rusty Days. I'll be uploading some of the archive talks, some of the older talks from last year onto the YouTube channel as well. So you'll have the added bonus of being able to go back over some of the amazing talks of last year and check them out there. So it really does pay to subscribe to the YouTube channel, Rust London, and also follow us on Twitter. Right. So just wanted to share my screen again. And just to remind everyone, we will now be heading to the Discord channel. So the Rust London Discord channel, if you're already on it, you can access it via your device or your laptop. The link is in the description. It's also in the chat as well. So the speakers, myself, a bunch of other people just going to be in the room chatting. You can ask more questions. You can interact. You can network with each other and continue the vibe, really, continue the conversation. So thank you all very much for coming. A big thank you to our speakers, crab emojis, clap emojis, fire emojis for our speakers. Tyler, Eric, and Alec, thank you so much for your talks. All of their slides will be available in the next coming days as well. And let's not forget our sponsors, TrueLayer. Thank you for hosting us through Zoom and also providing support through Slido. So a big thank you to TrueLayer, and we'll see you all at Rusty Days. So please, please, please check out the website for Rusty Days. Sign up, it's free, it's online. There'll be 7 days of talks, and check them out there. Thank you all very much and have a good evening.